So it's now 1 minute after 4 o'clock Central European time, and I think it's time for us to start the webinar. And we actually got a little sneak peek of the speakers, so they are eager to go ahead, so I think we better get going. So I would say a warm welcome to this webinar, and this webinar's got the title, Learn How to Develop Gesture Control Applications Using Radar and Edge AI. And this webinar is arranged by Imagimob. So it's great to see that we have so many that wants to learn the latest and the greatest about how to develop these gesture control applications. We're really pleased to have all of you here today. And before I introduce the speakers to you, I just want to inform you that this webinar will go on for approximately an hour. And in the end of this webinar, we will do a Q&A session, so you can get answers for all your interesting and nice questions. This questionnaire thing or question functionality, you can access it in the GoToWebinar control panel. It's easy to find. You just type in your questions there. You can type in your questions whenever you want. And we will, of course, do then our best to answer in the end. The rest of the participants will not see your questions, so please don't hesitate, ask the questions whenever you want during the webinar using this functionality. So I guess it's time now for me to introduce today's speakers. So we have with us two great speakers, Alexander Samuelsson, and he's the CTO and co-founder of Imagimob. And we also have Sam Atia, head of projects and customer group. So Sam and Alex, are you there?
Yes, we are.
Yes, you are. Camera and sound and everything. So please introduce yourselves.
Thank you, Lars. My name is Alexander Samuelsson. As Lars said, I'm the CTO and one of three co-founders at Imagimob. And I lead the development of Imagimob AI, which is an end-to-end service for building Edge AI applications, which we will take an in-depth look at today. And when founding Imagimob together with my co-founders in 2013, I and the rest of the guys had a very strong belief that AI should be moved away from the cloud, where it resides today, towards the edge, onto the actual devices and sensors where the data is generated. Because if you do that, if you move the application there, you get a lot of benefits, and you can build applications that you simply can't build if you deploy the AI in the cloud. And one of those applications is what we will actually build together in this webinar. So by processing and running the AI locally, you can react to your world, surrounding world in a few milliseconds. So you can create truly real-time applications, but you can also make those applications battery powered. And I've been involved in more than 25 Edge AI projects in some form since founding Imagimob. Some of them all the way from collecting data to actually deploying a commercial Edge AI model in the wild. And I was part of delivering one of the world's first commercial Edge AI models in 2018, where it was running inside of a watch for the elderly to detect falls and warn their relatives. And that's a real product that is using Edge AI from Imagimob. And another example is what I've helped develop through the development of our tools, which is an AI model running inside of the world's first gesture controlled in earphones. And that application is very similar to the application that we will develop together today. And on my side here, I have Sam.
Thank you, Alex. So I'm Sam Alatia, and I'm head of the projects and customers team at Imagimob. So what I do is I actually lead the customer support and the project development. So I work a lot with the customers and figuring out what customers want and helping them build the perfect models. So during my time at Imagimob, I've worked with many end-to-end customer projects. And what I mean by end-to-end is going all the way from the data collection planning all the way to actually building a model and then eventually deploying it on a hardware device. And that could be regarding the hardware part, it's typically demonstrators and proof of concepts. Yeah, so I work a lot with the software part, the firmware part, and the hardware. And my background is in electrical engineering.
Okay.
So great. Now you're introduced. So I guess you're take it from here now, guys.
Yes, let's get started. So before we jump into actually starting building the application today, let's walk through the tools and the different components that we will use. So first of all, to accomplish this, we're going to use Imagimob AI, which is an end-to-end service to build these kinds of applications. And by using Imagimob AI, a single engineer or a small team can build edge AI applications, very high performance applications. And these applications can be developed very quickly. So this application that you will see today, and the first time we actually built it and put it on this sensor, it took us 6 months to get a first demo like this in place. So this really makes this process much more streamlined. And here on the screen, you see all of these different steps that we will go through today. So first, we will collect and annotate high quality data from a radar sensor. I will soon show you how this sensor looks. Then we will manage this data into different data sets. We will also look at the data inside of the tool to understand it. And then we will build and train great AI models. And we will look at one of those models to evaluate it and assess that it's good. And then we will select the best model and optimize and package it for running on the actual hardware. And the final step that you don't see here is that we will actually show this model running on the hardware in real time so that you can see how well it works. Exactly. And at the end of the webinar, you will have all the knowledge and you will get access to all of the tools to do this yourselves. So you can replicate this exact application yourself. And we have customers already today using this tool to build radar control applications using radar. So, but you are the first larger group of people that we open this opportunity up for. So what I want to emphasize here is to stay to the end of the webinar because then you will get the full access to Imagimob AI. You will get full functionality. And the 10 first of you to sign up will also get the radar development board for free. Right.
Exactly. And then with the radar development board, you will have, in cooperation with today's webinar, you'll have everything that you need to actually build your own models.
And run it live.
Yeah.
So let's have a look at the setup and the different components that we will be using, and then we'll jump straight into it. So first of all, on the top, on the bottom right corner of the feed here, you can see the actual radar sensor. So this is the world's smallest pulse coherent radar sensor.
That's the radar there.
It's made by a company called Acconeer, and it's extremely low power, so it fits very well with the low power, small resource AI application that we will build. So this radar, it's mounted on a development board, and then it's connected to our PC here through a USB cable. So that's the device that we will use to collect the data. We'll perform gestures in front of it. And then we will capture that data using a terminal application that you see on the screen here. And once we have captured some data, we will move over to Imagimob Studio for the rest of the steps in the process. So in here, in this application, we will look at the data and build models and take you through the whole process. So what do you think, Sam? Should we get started?
Yeah, let's jump into it. So yeah, we have this application, and this is kind of an integration with our capture server for the Acconeer radar. And this tool is actually, we've created an open source, so every person can use this or create their own custom integration if they want to integrate with different sensors. So what we're doing now is we're running this Acconeer radar local capture server and then setting a path to store the data, passing in some sensor configuration file, and then choosing the UART connection and the camera. And the camera is, we will show it later what it's used for, but it's a vital part. So let's run this.
And all of this configuration and the instructions will be available for you after the webinar. Yeah,
so this is based on our tutorial project, which is available to all our customers. So we can see that it's started now and it's recording the video. But to actually save the data, we have to hit R. So you can see in the commands here show you what you can do. So let's start the recording. And now we're actually collecting data. So let's do a wiggle gesture. And then vertical finger rotation, and then a push. And these are the 3 gestures that we'll be showing today. So let's do it again. Let's do it in a different way. So vertical finger rotation, push, and the hand wiggle.
Let's get some data from A2, Sam.
So once we're done with the data collection, then we hit the stop button, and now it actually saves the video. And then we can jump into the studio application.
So now we're actually done with the first part. We've collected some, we've collected some data from the device.
So the first thing to do is to actually load the data. And this is the file that, so we've loaded this project and now we have this new folder of the data that we just collected. And we can see that it's with the time now. So maybe Alex, you can talk a bit about the studio while I import this data and start to label it.
Yeah, so all of the file formats that we're using here, they are open standard file formats. So it's of course easy to import data from that was collected using our tools, but it's also easy to collect or import data that you collected using other tools or data sets that you have found online. But what you see here now on the screen is the recording session that we just made in front of the radar sensor. And as Sam told you, we collected both the data from the radar, and that is the plot that you see here moving across the screen in the different colors. So that's the actual raw sensor data from the radar sensor. But we also collected video from a camera attached to our computer. And that's really powerful because we can now see, we can look at the video, we can play back the data and understand what gesture was performed, because it's impossible to see that from the actual data. And this is a very powerful concept that we keep through the process inside of Imagimob Studio. We put all the data that we collect on this timeline so that you can visualize it, you can play it back, and you're later on going to see how this is really powerful for actually investigating how your AI models that we built later performs.
Yeah, and we can see, especially now, how vital it is, where the vertical finger rotation actually looks like the unlabeled data. So here we have no data, and then we have vertical finger rotation. If you only had the data, then you wouldn't know that the gesture actually occurred.
What we can do is we can also change the visualization of this data and look at it maybe as a heat map, just to see if we see. Now it's still very difficult to see what gesture we're actually performing.
But later on, when we actually process the data in a nice way, we'll see that you can actually make some distinction.
So what Sam did here was that he added labels. So you see this track here in the bottom of the screen with these blue labels. Now a new one appeared saying push. What Sam is doing now is that he's annotating this data. He's telling the software which event is happening at the given time. And then later on, the software will help us to use this annotation to build the AI models. So the idea here is that you don't have to be an AI expert. You don't have to know much about AI at all in order to go through this process and annotate the data and build models.
Exactly. So we're almost done here with the labeling. We just have one last label to go. I think that was, no, that was, yeah, a wiggle. So there, we've labeled all the data, and then it's just a matter of saving it. Now we can go to the next part. So once we've labeled all of our data, and here you can see that we've already collected some data beforehand. The data collection part is actually the most time-consuming, I would say. So over here, we collected the data for the wiggle gesture, the push, and the vertical finger rotation. We also collected some random data to train the model not to trigger, and some combined gesture data so we can look at what happens when you transition, like in this video.
So what you usually want to do here is that you want to collect data from a number of different people.
Yeah.
So that your model can understand that people perform these gestures slightly differently.
Yeah, and for this project, it's actually supposed to be a startup project, so it's only set up for one person. So we'll see that there are some false positives when we go to the live testing, but it's so you can build on top of it and expand it yourself.
Yeah, so what you see here in this view is that you see all of the data that we've collected previously. And now Sam will add the data that we just collected into this project.
Yeah, and you can actually see that I made a mistake here.
So you misspelled one of the labels, so we got a new gesture. We got 4 gestures now.
Yeah, maybe this is a good time to talk about the classes that are shown here.
So what you see here in this view is all of the recording sessions. And on the right here, you see the different gestures, actually the labels that exist in each of those files. So we have 3 different gestures, but since we mistyped one, we got 4 different gestures. And now the software actually spotted that error and is warning us that, well, one of these gestures only occurred once. Because in this view, you can also see this set column. So then when you add the data to a project, it gets distributed across 3 different data sets, which we will soon get into and explain. But before we do that, we can go back and correct this error.
Yeah, and you can see it further here, where we see that we have this vertical, which is supposed to be vertical rod for rotation. It only has 1 label, and it's only 4 seconds and 0 for the other categories. So let's go back to this, and it's actually not this one. It's actually this one. So let's fix this, and then we'll save the changes. Now, let's, normally you can rescan, but it takes some time to scan everything. So I will just delete this one and re-import it. And then we just, oh, what's happened?
I think you might have to remove it from the symbols, or do we? Let's rescan.
Maybe I didn't save it. So, okay, let's go to the symbols. So now it detected that there's no data for that symbol. And then let's re-import it.
So this view is a great help actually making sure that all of your data is consistent and well distributed, and it contains no errors. So if you had, for example, different frequencies here, or you have files that are not annotated, you get warnings for that. So there's a lot of things that can go wrong with your data in an AI project. So having this as a help, confirming the data, is very powerful.
Yeah, and you get, so by sorting this, we can see if there exists errors or warnings for specific files. And in this case, we see that there are no labels in these files, but that's expected because they're supposed to be empty and random gestures. So it goes into the unlabeled class.
So now it looks fine.
Yeah, so this is the file that we have, that we collected. We can see that the name matches, and now it has the right configuration. So let's go on. And now what we're looking at is the distribution for the different sets. So when you first import the data, it assigns to a random set, but then you can fine tune this with this in this window, for example, to set the target sizes. By default, it's actually 60-20-20, right, Alex?
That's correct. And maybe we should talk a little bit about the purpose of these different sets.
Yeah. So we have the train, validation, and test set. And the training set makes up the majority of the data. And that's what you actually use for training the model. And then you use the validation for fine-tuning your hyperparameters, and so it's inside the training process. And then finally, when you're done with the training, then you test your model on the test set.
Yeah, so you can look at these sets as the purpose of the test set is to see how the model behaves on data that it has never been optimized for in any way, meaning it simulates how this model will behave in the real world.
Exactly.
Seeing unseen data.
And you can build on top of this concept by having special test files that you include in your test set. And they could be things with random gestures that you might think would be close. For example, a waving gesture, to see, okay, I've trained on these gestures. I only wanted to detect these 3. You don't want it to pick up random gestures as these false ones. So that could be something interesting to add to the test set. And in the end, having an extensive test set helps you save time by not needing to actually test the model in a live scenario every time. be more confident.
So starting out here, you have really good presets and default values, and then you can tune it any which way you want.
Exactly.
But let's move on to the next tab, the symbols.
So we've looked at this before slightly when we were removing the false class that we mislabeled. But maybe you can talk a bit about this, Alex.
So the purpose of this tab is to give you an overview of all of the data that you have. So what you see here is how much data we have from each different gesture in this case. And what you typically look for in an AI project is to have a balanced data set. So you want typically as much data, the equal amount of data from all of the three gestures in this case. But you can actually look at the data in different ways. So here we see it in time, how much data we have in each gesture, in each data set. But you can also look at it by the actual label count, for example, to see how many occurrences of a label that we have. But so here you get this overview, this quick view. But you can also go in here and you can change the weight for the different classes. And that can be really useful because you might have a gesture that is really easy for the AI model to learn because it's simple and easy to perform and everybody does it the same. And then you might not need to put as much emphasis on that class. And here you can see with the push gesture, which is a very simple gesture, that we put a smaller weight on that class compared to the others.
Yeah. So this is kind of a bit different than what you'd expect, because by starting out, you should set this to 2 so that it has double the weight during the training process, and that balances it out with the other classes. The reason why it was actually trained with 0.5, and this is, we will see this a bit later, is that the push class is actually a lot easier to detect than the other 2 classes. So in the end, the model actually picks it up very easily and then ends up leading to some false positives. So by default, you want to pick a ratio such that all the classes are balanced, but then there's lots of opportunity for optimization.
So this is something you typically play around with during a project.
Yeah. So let's go on to the next part. And now we're actually up until here, we're actually dealing primarily with data and labels. And then the next part, we're actually going to go into the first step of the model building process.
That's true. So this is a part that us engineer really loves, of course. And this pre-processing tab here, it's a well-kept secret for succeeding in an edge AI project, because what we're doing here is that we're pre-processing the data, looking at the data in a different way compared to just looking at the raw data that we showed earlier. And we will show you how this looks. But by adding a good pre-processing pipeline in front of your AI model, you help the model.
Yeah.
So that has 2 benefits. I mean, with good pre-processing, you can get away with collecting a lot less data, and collecting data is very expensive typically. It takes a lot of time. But you also end up with a much smaller model with higher performance. So it will use less memory and less processing power on the device. So we have put a lot of effort into this part of Imagimob AI. And if you click on the plus symbol here, Sam, you see that we have a library of pre-processing functions which you can use. You stack them together like Lego bricks to get this pipeline, and you can combine them in many different ways. But you will get access to the pipeline that we've built here. So we have already a really good pipeline for this particular sensor.
Yeah. So essentially everything that we will show here, you all have access to once you sign up for the free trial.
So maybe we should talk a little bit what we do actually in this preprocessing pipeline.
Yeah, so what we do is we actually reshape the data, and this is actually after the reshape, that's actually the output of the sensor. We flatten it to have it in a nice CSV format. So we have 1 row per timestamp. So we're just reshaping it back to the original form. And then we perform a bit of cleaning on the data. So with the average subtraction to normalize it, and then the Hon smooth it to apply some filtering and to make it better to work with. And then we apply a Fourier transform. So up until this point, we're dealing with time domain, and then now we're actually converting it to a frequency domain. And then what we do is that we take the magnitude, because the output of the Fourier transform is a complex value. So we take the magnitude of that complex value. And then we end up with this 33-3 shape. And what this is actually showing at this point is that the radar works in a way that it collects data at multiple distance points. So this is actually showing us that for 3 different distance points, we have an array of 33 frequency values and magnitudes. So what we're doing in this step is that we're summing the outer dimension, so the distance point, and then so you have data that's a bit further away becomes also prominent if you move it forward, because then it doesn't matter on which level the data actually is.
Exactly. So the purpose is to get the same pattern if someone is performing the gesture close to the sensor or further away.
Exactly. And then the last thing is that we are summing up a set of values over a period of time. So what this is showing is that we're taking this this output, and this output is for every timestamp. So every single sample, you have this vector of size 33, and we are combining data over 78 time points. And with the sampling frequency that we have, which is 39, this means that we're looking at 2 seconds of data.
Put 2 seconds of data together and let the model classify that.
Exactly.
But now we're going to look at this preprocessing, right?
Yeah. So if you would want to visualize it, and for the visualization aspect, you want to visualize for every single data point. So you would remove the sliding window, and then in this case, we have shown that here. So we have the exact same processing, but we remove the last value. So we do it for every time point, and we do it for only two of the most interesting data. And we can even add the one that we actually collected now. So let's do that. So then you would hit the create track. And then it's now applying this processing to the data. So yeah.
And the processing takes some time, but there it's done.
Yeah, and then so once it's done, you get this new folder called Preprocessor track, and then you can open it up. And then what we see here is that we have now generated the frequency transform for this data. So what we can see here is the original data, the new processed data, and then the original labels.
So what do you usually look for here, Sam, to know if your preprocessing pipeline is good or not?
Yeah, so the most important thing is actually separation between your classes. And this goes for everything, not just gestures. You want to be able if you can find the distinction between the different classes, then the model will be able to as well. So over here, we see that the push is very prominent with a unique feature. And then we see that the wiggle is also, it's a bit hard to see on camera, but it also has some properties. The vertical finger rotation is a bit weaker, so what we see here is the time domain, the frequency, and the color represents the magnitude at that frequency. So this is my vertical finger rotation. We can go to the end and see if Alex's is any different. We can see that Alex is actually better at doing the vertical finger rotation. I see that it's a bit better, so it kind of starts off small and then increases and then goes down a bit.
But zooming out, you can actually see that there are similarities in our gestures. So if you look at the push, it's similar, but mine is a little bit weaker in the intensity.
Yeah, and similarly for the wiggle.
So this means that we probably have some pretty okay pre-processing here.
Yeah, but I would say that it also means that it can be improved a bit, perhaps because we can see that the majority of the frequency spectrum is actually not utilized. So some kind of scaling of the values would be very beneficial, and then you would make the vertical rotation more prominent. So once looking at this, you can decide if you're happy with the processing or not, and in this case, we want to go ahead with it. So we go back and we want to commit to this, and then we go to the next step. And this step is the actual model generation part, and maybe you can talk a bit about this, Alex.
Yeah, so our vision when we designed Imagimob AI was that anyone should be able to create really good edge AI models. So we have a auto machine learning functionality in here. So using the software, and Sam will show us, you can follow a little wizard here, and the software will actually generate a list of different models that will work well for the data that it has as inputs. So we put a lot of work into creating an algorithm that can generate models that will work really well and have a really low footprint. So the idea is anyone can use this to build really good models, but we still want to be transparent, and we don't want to limit AI experts. So if you're an expert, you can go into any of these models, you can look at all of the parameters, and you can change them and remove or add stuff yourself. So that's what we believe in. Everyone should be able to use it, but no one should be limited by it.
Exactly. And you can also add your own layers.
So, but let's go ahead and generate a list of models.
Yeah, so let's, so what we're doing now is we're going to select that we want a combination of two generated structures with two, each structure having two sets of hyperparameters.
So a structure in this case is a neural network. So the kind of models that we're working with here are deep neural networks, and different model structures, they will be different depth and different kinds of layers in different combinations. And then, as Sam said, each structure can have different parameters controlling how fast it learns, how well it should generalize, and how quickly it should forget things it learned in the past. So by setting these this first value to 2 and the other to 2, you will end up with 4 models in total.
Yeah, exactly. And these generated models, they're based on our experience with building AI models for many different projects. And then the last thing is that we have the label strategy, and we won't go too much into that, but the most frequently used one should be the default, which is most frequent. It's not called that for that reason, but
we're gonna stick to the default, but you can read more about it in our documentation.
yeah. So let's go ahead and do that, and we expect that there will be 2 times 2 sets of models. So now we see that we generated 2 different structures, one with the LSTM and then one without. And then we have 2 sets of those.
And these models are actually fairly complex. I mean, they contain some complicated layers, but you will see that we are able to optimize them really well at the end. So exactly. What's the next step now?
Yeah, so once you're up to this point, you're essentially in the clear and you can start training. So we'll go to the next tab and we will start a new training job. And then you can change the job name if you would like to and the description, but we will go ahead with the default. So let's start this training. We'll log in. And then it's uploading the job to the cloud. And so this will upload the data files, the labels, and the pre-processing information. Right, Alex?
That's correct. So everything goes to our cloud service. So you can train a lot of different models in parallel, and you can do it, during night. You can use your computer to work on other stuff without using any of your local resources.
Yeah, exactly. So you could try out different processing, you can try out different weights, you can try out different sizes for the sliding window and then run them in parallel. So now we are uploading this, but let's look at the one we already have. So you can see that now this job is starting, but it will take some time. Let's look at something that I've already trained, and in this case, we're showing I trained 25 models, and so that would be 5 times 5. And let's go ahead and sort them by the test F1 score. So what we're showing here is that we have the performance metrics for the train validation and test set, and we have the accuracy and the F1 score, as well as the number of parameters, so you know something about how big this model is.
That's very useful to know in advance that it will fit in your target device or not.
Yeah, and then you can look at each model a bit in depth. So just by selecting it, you get this confusion matrix.
So what do you usually look for in order to select the best model?
Typically, I take the one with the best F1 score because it's a good summary of all the different performances. But I do also, if I have, such as in this case where you have 0.91 and 0.90, then you might also want to look at this is actually a third of the size. So that's important. You also might look at what are the weaknesses of this model. For example, let's look at the test set. In this one, you have the vertical rotation is not very good, whereas for this one, it's about the same. But this one also has the some weakness in the wiggle versus the vertical finger rotation.
So what do you actually see here in this matrix here?
Yeah, so what we're having is the actual label at the top. So we have the push, vertical, and wiggle, and that's what we actually labeled the data. And then we have the predicted model. So what you want to have is a very high green diagonal line where it's classifying the correct prediction for the actual label and the low value in the other locations.
So if we mark this cell here, we see that here is where this data was actually labeled as vertical finger rotation, but the model misinterpreted some of the data as wiggle.
Yeah, exactly. And then you have a lot more information about the model performance. You also have some loss and accuracy plots to get an idea of how the training went.
Hello guys, this is Lars. I have a question actually that I think it could be great if you can answer immediately now. I'll check with you what you think about it. Is it possible to estimate requirements to MCU resources on the step of processor and model design at this step?
You can get a rough estimate by looking at the amount of parameters. So if you have gone through the process and built some edge models and put it on the device, you will have a good feeling of what this number of parameters means in terms of actual memory used and inference time, which is the time it takes the processor to make a prediction from when data comes in. So yeah, you can use these numbers to get a fairly good estimate. And you also get a more detailed report at a later stage, which we will get to.
Perfect.
So Sam, what do you think? Is this the model that we should investigate further?
Yeah, so let's pick the top one, and then what you would do first is download the evaluation, for example, into the results folder. And here I've already done it, so let's go ahead and open it. So we want to close the modeling and the data. So let's look at this FFT folder, which is for the rate processing that we just did, and then we have the data files. So let's look at one of them. Let's look at this combined gesture one, which is interesting.
So what we're doing here is actually we take it one step further than the standard machine learning metrics, and we let our compute service, our cloud service has run this model across all of the data that we collected, so that we can see exactly how this model performed while it was running in real time.
Exactly.
And then we put this again, we're using the timeline paradigm, and we're putting it all in the timeline so that we can look at it in detail and play it back. So what we see here is still at the top, you see the sensor data from the radar, but we have some other data here, which is actually the raw output from the model. And we're not going to go into detail about that, but that's actually you can see how confident the model is about the different gestures being performed at that time. So here you can see that it now thinks that the vertical rotation is being performed here, and over here when the red one is the top, it thinks that the wiggle gesture is being performed.
Exactly. And so let's go back to the original data, and then maybe we can talk a bit about what we see here at the bottom.
Absolutely. So let's zoom out to get a little bit of an overview. So what we see here at the very bottom, the lowest blue label track here is our original labels, the one that we labeled at the beginning manually. But above that, we see two new tracks, and those are actually the predictions by this model on this data. So what Sam is highlighting here, so we have two different versions of that. We have the raw predictions, and then we have the merge predictions. So let's start with the raw predictions. What you see here is every single prediction that the model makes. And we talked about this earlier. We put everything, all the data in a window, and we let the model classify that. So here you see the individual 2-second windows and how the model has classified them as being different gestures. The track below it is those predictions merged. So then we merge all the windows, adjacent windows with the same prediction together into one larger label so that we can get a better overview and easily spot when it moves from one prediction to another.
Exactly. So we can see here that there are some false positives, and they are a bit hard to see when you have an output for every single window. But when you combine those similar windows together, then you can see that here you have a transition, and then here you have a transition back to the correct label. And you can see that there is another here. Whereas for these other occurrences, everything is fine.
And what we can also do here now actually is we can play this file back and move to the beginning here.
Okay.
And now you also see that we get subtitle, which is what the model predicts. So you get that on top of the video. So what you can do here is you can really perform a field test in front of your PC. So this is extremely powerful. You can look at how the model behaves even without deploying it anywhere.
Exactly.
And actually, quite often you can figure out that you've mislabeled the data while looking in here.
Yeah, or you see that the person performing the gesture is performing it in a different way than maybe what the model was trained on. And it's not so uncommon, especially when you're talking about gestures, and it's very hard to actually communicate what you want the person to do.
Mm.
So when you're at this point, you have two pathways. One is to go back and improve the model if you're not happy with the performance, or if you're happy with the performance, the next step is to proceed forward. So let's go back to our original training job. And what we did was we downloaded the evaluation. Now we want to proceed to the next step and actually download the model. So we're just downloading a .h5 file, and we want to save it to our results, which I have done. So that's this model here.
So yeah, so what do we see here, Sam?
Yeah, so what we're seeing is exactly what we did before. We have the processing, which we trained the model on, and that's built into the .h5 file. Then we have the actual network that we generated, and this is the best network, the one that we selected. And then we have some built-in metrics to help us keep track of the different models. And then the most interesting part is that once you have the model, you can generate the C code. And what we do is we actually generate the C code for the network layers, but we also generate the C code for the processing that's included in the studio.
So this is something that a lot of frameworks forget. They have a way of optimizing the actual network part of the model, but forget that to optimize the pre-processing part, or even have a pre-processing part that you can actually run on an embedded device.
Yeah, and running an FFT in Python is fine and easy, but running an FFT in C code is not so easy to write. So it's not something that you can do in an afternoon. So, okay, we have this model. Let's go ahead and build the C code. So we hit the build edge, and now it's complaining that we already have it, but we want to overwrite it. And now we actually finish generating the C code.
So here we see what we were talking about earlier. We see the exact memory footprint. So we see how much RAM and flash will be used by this when we deploy it on an actual device later. But also want to stress that this step, before we had this in place and we would convert these AI models ourselves into C code, that could take several months just to convert a single model manually into C code. And now it takes a second.
Yeah, exactly. And it's also, you have a guarantee that it will work. It's already pre-tested with lots of our automated testing. And this model is all right. It's 45 kilobytes, and that's a bit big for embedded devices. So what I went and did just today is that I generated a reduced size. So I got to this point, I wasn't happy with the performance, and then I went back. And what I did was that I reduced the sliding window size from 78 to 27. And so that's about 0.7 seconds. And our gestures are actually very quick, so that's not a problem. And then I generated a new network, trained it, and then evaluated it. And here we can see that the performance is a bit worse for this one because it's a lot smaller, or it looks at less data. But then you'll see that we will test it on live with Alex, who has actually never been included in the training set. And I haven't been included in the training set either. It's just the test set that I've been included. So let's go ahead and build this new model. And yeah, so we have 15 kilobytes, which is a lot better than 45. It's about a third of the size.
So this illustrates how powerful it is to get the pre-processing right. So by slightly adjusting our pre-processing, a much smaller, more efficient AI model.
Yeah, and it's essentially I just changed one value. And it also demonstrates how important it is to actually have a tool where you can make these minor modifications and have everything be standardized and automated.
That's the power here, that you get a really quick feedback loop where you can build, evaluate, and then rebuild.
Yeah.
So now we have some C code.
Yeah.
I guess we're going to have a look at that. But we're very close to the last step where we'll actually put this on a device.
Yeah. So we have this C code, and that's not so interesting. This is just automated C code with lots of weights and other things.
But what is interesting though is that it's completely self-contained. So it doesn't depend on any third-party libraries or routines. So you can take the C code and deploy it on any compute platform in the world.
Yeah.
As long as it can, run, it has a C compiler,
yeah.
which is essentially every compute platform in the world.
Yeah, and we're using C99, so not any kind of modern version. But let's look at the header file to show how easy it is to actually use it. And what we have is just three functions to call. So we have an initialization function, an enqueue function where you pass the data, and then a dequeue function where you read the output.
So that means that it's really easy to include this model into your firmware.
Exactly.
And you have an example of that, right, Sam?
Yeah, so let's actually see how you can include this model in your actual firmware. So I have this Acconeer SDK that I downloaded, and I just built some documentation, and this we will provide to our customers. So let's go into this SDK. I only added two things. So I added this folder with the model that we just converted, and then I added this header file, filled in the wrong version. So yeah, and what I did here was that I updated the configuration to match the what we have, and that was just a couple of lines. So I essentially set some values with my configuration and then passed them using the Acconeer's API.
So this is all Acconeer sensor specific.
Yeah, exactly. And then now, it was actually in the same file. So let's go to the example project, and it's in this for loop. So this is the main loop, and what we do is that first we initialize the library. So I just called it somewhere at the beginning, and then we just before that we updated the sensor configuration. And then this is the actual main loop where you're reading the data, and what I do is that I pass the data using the enqueue function, and then I compute the output using the dequeue function. And it's just a matter of setting up these two function calls with one argument.
And then you take that output from our library and look at the confidence level of the model for the 3 different classes.
Yeah, and I compare it against some threshold that I tune depending on the performance of the model.
So and this is what we will run on the device, and here is the prints that you will see when we run it live, depending on the different classes. So essentially 10 lines of code to integrate this model into the firmware for an Acconeer device.
Exactly. It took longer to actually find the code. Once I dug through the SDK, that was just a matter of adding the simple functionality for it to work.
Okay, so now we've added it to the firmware. Now we're gonna test it out live on the actual device.
First things first is that, and this is, as I said, available to customers. And then once you have this this file, then it's just about running the makefile to compile this hex, and we pre-flash it onto the device.
Okay, so what we do now is that we switch over to the other device that we have pre-flashed.
So this was the original that we used for the data collection, and we have a different version that's pre-flashed.
And now what we will do is to connect to the device.
And then we're setting up serial communication so that we can read outputs. And then now we're connected and everything should go. So let's try a wiggle gesture. And we can see that it shows up. Let's try vertical finger rotation. Now let's do push.
So that's how you go end-to-end in building an Edge AI application and actually deploying it on the device.
Exactly.
So what you see here is, of course, the detected gesture, and then you have a number next to that. What does that mean, Sam?
Yeah, so what we're seeing with the number is that's the confidence level for the gesture, and that will help you to fine-tune it. If you see that actually all the correct gestures are above 0.9 and all the wrong ones are below 0.8, then you could raise it even further.
So let's see if it works for me as well. Push detected. Finger detected. Wiggle detected.
And yeah, so for a proper project, you want to go, you want to collect data from many different people because they would probably do the different gestures differently. But this is supposed to be just the starter project as a demo, and it's only collected with one, and it has a bit of data for me for the validation and the test set. But we've tried out actually this exact project with more people, and it performs a lot better.
So now we've gone through all of the steps that we want to show, and I think it's time for the Q&A section, Lars. But before that,
yeah, you promised some goodies in the end.
Yeah, exactly. I should talk about the goodies. So you should stay to the end to get full access, and you have stayed to the end. So here you should go and visit our webpage, imagimob.com, and there's a button there where you can register for a full access free trial, and then you get to a form, and you should the form says description, and there you add gesture webinar in the description box to get access. And again, the 10 first of you will also get the board, so that you can collect data yourself and test everything out live. Yeah.
Okay, so time for Q&A. And we have received a number of questions, and we will of course do our best to answer. And of course, you can still type in questions. I just want to inform you that tomorrow you will get an email with some more details regarding these things and contact details, and also recording of the actual webinar. If everything goes well with the technical side of things here, but I think it should. So look out for that in your mailboxes tomorrow. So we're going to move over to Q&A, and it's now 7 minutes after 5 o'clock Central European time. We will continue to do the Q&A for another like 23 minutes, and then we will close down the webinar. If we still have questions that we're not able to answer, we can come back to you and answer them afterwards, because all your questions will be saved in the system. So let's start, and it starts real well, guys. The first question, I just love this. And a comment on that: data collection is the most challenging and boring task. So that's apparently good. And then we have another question. So I think you actually touched on this one. It was kind of covered, but still it's a relevant question. How are you doing with radar? Can you do this with other sensors? Yeah, so now you're doing it with radar. Can you do it with other sensors? Yeah, I guess the answer was there, but maybe you can just make it clear.
Yes, absolutely. So we showed this little application to collect data with in the beginning, and that's open source, and we provide examples for the radar sensor, but we also provide an example where you can have a look at how you would integrate any kind of sensor into that application. So yeah, you can collect data from any kind of device, and as long as you can connect it to your computer over serial. We also have a capture app, a phone app, so that you can collect data from some devices wirelessly.
Okay, so yeah, so good. Thanks for clarifying. And some of these questions, they come from a relatively early part of the demo, but this one is sort of, is heat map the spectrogram of the data? You remember what we were showing there in the beginning. Is the heat map the spectrogram of the data?
Yeah, so you can actually choose. There's two different view modes. So either you have the line plot where you see the lines, the data as lines, or you have the heat map where you see the data as a heat map. So you can look at the original sensor data as a heat map as well. But Sam, maybe you want to elaborate.
Yeah, it was actually the spectrogram when we converted it to the Fourier transform.
Exactly. So it makes a lot of sense to use the spectrogram once you run the data through a Fourier transform.
Exactly.
Okay, here comes a little bit longer question. So so here it comes. You labeled the first rotation as vertical root, and the second instance as only vertical. Does this make any difference? Is it intentional to have different names of same action?
Yeah, so That's a very good question and well spotted. That was a mistake.
Yeah, exactly.
Yeah.
And that's actually very typical of the mistakes that it's kind of human error and it's expected. And sometimes that's actually what leads to some discrepancies in the performance metric. Because it could be that somebody was, after collecting many hours or labeling many hours of data, you can go into like robotic mode and you end up mislabeling data. And that is a bit of a problem.
So that's what we saw there in the segments view in the beginning. We saw by creating a label there with a different name, the software thought we now had a new gesture, but we only had one occurrence of that gesture in the entire project. And it warned us because that gesture only occurred then in one data set because there was only one of it.
Exactly.
So that highlights kind of how important it is to have good software that helps you getting an overview of the data and spot common errors.
Yeah, exactly.
Yeah. So it helped you actually deliver something that's more error-free in the end.
Yeah.
Okay, interesting. Thanks for that. Well spotted. So next question, what is combined gestured data? What is combined gestured data?
Yeah, so maybe we can go back to the studio. So essentially what we did, and we didn't dig so deeply into it, is that for the normal data, let's take this wiggle sound, what we did was and this is described further, so this project is based on a tutorial and is documented. So what we did was we made the whole video as one specific gesture, and what we did was that we ran an automatic labeling script. So since the whole video is only one gesture, you can immediately detect when the activity goes above a certain threshold and then apply a label for the entire thing. This doesn't give you a realistic view of what the data looks like. So in the test set, it's not so great. And then we go back to this combined gesture. So where we actually combine the multiple of them.
Okay, so fine, thanks for that. We'll move on. This is also a relatively long question. Is data augmentation inbuilt in the tool? Can we work on the already recorded data to create titled, rotated, mirrored push actions, just for example? Or should the titled, rotated push actions be recorded again?
That's a very good question. So one way to make processes like that simpler that we have in place is that you can actually integrate this tool with scripts, Python scripts that you write yourself, and then you can apply those scripts to your data. So that's what you use to label the data. So you could have scripts like that you've written yourself to mirror the data and do data augmentation. But at this point in time, we don't have data augmentation functions built into Imagimob Studio, but it's in our roadmap for the future. But it's easy to integrate it if you have it yourself.
Okay, thanks. We'll move on. So here comes another one. Some cheering on here. Nice work, you guys. Does Imagimob support, and here it comes, FPGAs? FPGAs. Do you understand what this is?
FPGAs, Field Programmable Grid Arrays, or something like that is what it stands for. We don't support FPGAs at this point in time. So what FPGAs is, it's how do you say? It's programmable hardware. So you can easily program and test hardware that you're later gonna produce and see and try it on early on, the different designs. Or you can build an FPGA for production to do some task, run one AI model very efficiently. This is not something that we support now. This is something that we might support in the future. But now we generate C code that can be compiled and run on microcontrollers, not that on FPGAs yet.
Okay, thanks for that. And here comes a really long one, but I think this is an interesting one. The data was recorded from 0.06 M to 0.12 M with about 190 points within this range, if I saw it right. Did you put this data for training like one vector, one frame after another, or did you pick some particular range bins and took signals from the fixed distances?
I think you are very quick to answer this one.
So this kind of goes back, if I understood it correctly, this goes back to this point here where we actually collected the data at 3 different distance points. And this is the output of the Acconeer radar. And then what we did was we summed up the 3 distance points so that in terms of from the model's view, it doesn't care if it's at distance point 1, 2, or 3, and it will look the same to the model.
But this is a configuration that you make in the radar sensor, right?
Yeah.
So you can set it up exactly like the question says here. You can configure the radar to collect data from a bunch of different distances and put the data into bins. So each reading we get from the sensor is actually a small amount of time captured from 3 different distances.
Yeah, and you could actually do the step in a number of different ways. If you actually care about the distance point, then you could flatten it, as the attendee said. Or you could take the maximum instead of the sum. That would give you slightly different behavior, things like that.
Okay, another question that's also a little bit about the distances. Let's see here. Can you automatically select the radar range? If yes, how? Because the system will not recognize gestures if they are performed out of range.
So do you know if the radar is configurable to change the range depending on the data?
I think that would be a question best answered by Acconeer.
I think so as well. So there is, I mean, you can set it in a mode so that it looks at everything from the minimum range to the maximum range, I think. But one good reason for configuring a fixed range yourself like this is that you can you can use this bin mode, which actually uses less power from the radar. So this is a very power efficient way of doing it. Maybe you can do it in other ways, and you can go to acconeer.com and read more about this particular sensor.
Yep, okay, so let's move on. So what's the rough estimate of training time for the model we've just built in this demo, if you do it in reality, sort of?
We can have a look and see if it's done training actually.
Yeah, so I guess that's under you, Alex.
Yeah.
So yeah, so we can see that it's already done. So maybe you can give some rough numbers. I think normally when I run 4x4 for this project, it might take me less than an hour.
Less than an hour.
Yeah.
Yeah.
So typically when I'm showing the tool to customers, I pick some default value, and it's normally done. I mean, I think maybe we started at most 40 minutes ago with the training.
So let's say 30 to 40 minutes for this configuration. Okay. And then it varies. Adding more data will take longer, of course.
Yeah, and the sprite value ends up having an impact as well because you end up with more windows.
Okay, so let's move on. We have a couple of more questions, so hopefully we'll actually manage to end this in time. Can it be even more efficient if we extract some metadata from the radar signals from preliminary, such as distance to the max, reflection, and deviation? You understand the question?
Yeah, I think I understand the question. I think the proper answer for that is maybe. So what you're doing in that case is that you're actually, you're using your knowledge to generate features from the data source by, as the question states, converting that into a distance or a reflection. And if those features are good features that tells a lot about the gesture being performed, then that will be very useful for the model. Then the model will use that to create the mapping from the data to prediction. But that's what you have to look at when you're visualizing the data. If you, on the other hand, see that, well, that data is can't be used to distinguish between the different gestures. If you can't see any pattern like that, probably the model will have a hard time finding any patterns as well.
Okay, so let's continue. And if we don't have enough time to answer all your questions, we will get back to you afterwards. I can see there is more questions coming in here, so I don't think we actually have the time. So don't be worried, we'll get back to answers afterwards. But we have some more that we can cover. This is a pretty straightforward question, I think. What is the device piece? I think this means sort of what radar is it actually? Do you have the specification for the actual radar?
So this is it's the XB122 with an XM122 radar attached. So I think this is Acconeer calls a breakout board with the XM122 radar attached.
So yeah, I hope that answers the question.
Yeah, I hope so.
Yeah. Okay, and then there's another question about the device, I think. Have any cost? So the device, does it have any cost? I guess it has got some cost, or maybe this even means Imagimob Studio. Maybe you can answer both.
Yeah, so the device itself in this configuration, I think, is somewhere between, with both of these boards, so that you can develop, it's like somewhere between $70 and $100, right?
Yeah.
So there's quite some value for you if you register here now.
Yeah, register quickly.
But if you buy it in bulk, if you want to integrate it into a product and sell it in large quantities, it's a lot cheaper. I think the actual sensor itself at high volumes is a few dollars. Contact Acconeer for the exact numbers, but it's very cheap in large quantities. And Imagimob AI, if you want to continue to use it after the free trial, you sign up for a license and you pay per month. And it varies depending on how many users you have, but it starts at €1,000 per month for a single user.
Okay, let's continue. I think this will be the last question, but we'll see. Is it possible, meaningful, to have different window length time for different gesture detection?
The straight answer to that is you can't really have different windows for different gestures, because the window size is part of the model itself. So it will have a fixed window size. Actually, I don't want to go too depth into technical details, but it depends on if your model has a state or if it's stateless. So now we're working with a stateless model, and then you need to have a window so that you can present data over time to the model. You can also build models where the state is built into the model, and then you don't need to have a window at all. The model will kind of just feed it in single values over time, and the model gives a prediction when it has enough information. And those kind of models we are testing now with the tool, but they are not available in the released versions yet. But that's, for example, very useful if you're building a complex audio models, because then you have very high frequency data, and you don't want to have too large windows, as it creates, you end up with a lot of memory being used for those buffers on the device.
Okay, there's a couple of more questions, but I think we'll have to save them for afterwards and come back with answers. We have one question though that I think we need to answer. This has got to do with the link for the free trial. I don't know, maybe Alex, is it possible for you to go to the website and actually show the audience where the link is?
I think we can arrange that. So I think we can.
So while Alex is doing that, you will get an email tomorrow, and the link will definitely be there. And also, if everything goes fine with the recording, you will get access to a recorded version, so you can share this with others or look at it again. So we'll see.
So here, if you go to imagimob.com, you have this button here, sign up for Imagimob AI free trial. And then you scroll down a little bit and you fill out this form. And then here in the description box, you add gesture
webinar.
Yeah,
that is clear. The first 10 also get access to the actual device. Yeah. All right, so it's 28 minutes past 5 o'clock Central European time. It's time for us to say thanks and bye-bye. And so great to have so many with you and so many staying the whole time for this, the actual presentations, and then this long Q&A. So of course, big thanks for everyone that took their time joining today. Maybe some final words from Sam and Alex before we close down.
I also want to thank everyone who took the time to watch this. I hope you grab this opportunity and try this out and play around with it for yourself. And I want to thank you, Lars, for helping us setting this up and arranging all of this.
Yeah, thank you all.
All right, have a great time. Take care and be careful out there these tough pandemic days. So we'll close down the webinar for now. Bye-bye.
Bye.
Bye-bye.